Okay, so today's lecture, I would like to talk about the characteristics of logic gates. I also would like to introduce Verilog. So the outline of this presentation is like this. I'm going to talk about timing diagrams. I'll talk about the gate delay and the circuit delay. I'll talk about fan in and fan out. Okay, so these are the topics that I would like to cover in this presentation. Right, remember at the beginning of this semester, so I talked about the logic 1 and the logic 0. So logic 1 electrically is a range of voltage values. And for example, you might have logic 1 around 0.7 to 1 volts today. That's the amount of voltage which is needed to turn on, to switch on, let us say, a given transistor inside the circuit, inside the gate. So we need these voltages, okay, for the gates. Okay, and that's the representation of voltage 1. So it's not just a single voltage value, but a small range of values. The same thing can be said for logic 0. So we also have a small range here. Let us say not just 0 volt, it might be, let us say, between 0 and 0.2 volts. In between, there is an undefined voltage range. So the voltage range is undefined in between. Now, notice that when you have a signal, a digital signal, okay, the signal is going to rise, going to go from 0 to 1, or it's going to go from 1 down to 0. It has to pass through this undefined voltage range. So even though it is actually if it's rising or going down, still this voltage range is undefined. Okay, so either the signal is 0 or 1. In between, we say it is undefined. So we don't really use the voltage values in this undefined voltage range. Okay, so there is this gap between logic 0 and logic 1. Now, timing diagrams are very important. Okay, one would like to simulate circuits. Okay, I will talk about Verilog and as a hardware description language. I'll talk about how we can simulate circuits. So this is coming next. So in the case one would like to simulate a circuit, we produce timing diagrams. So the timing diagram is very important because it's going to show to us the logic values of signals versus time. Okay, let me show you, let us say, a simple AND gate that has a 0 delay. So the inputs here are X and Y. These are the inputs of this AND gate. And this is my output Z. Okay. Now, X and Y, their values are going to change over time. So suppose that initially X equal to 0, then at a certain moment in time, X is going to go up, is going to jump from 0 to 1. Later, X is going to drop from 1 down to 0, and so on. So X is changing over time. So we call this the waveform. So the waveform, it is the shape of a signal over a period of time. The same thing can be said for signal Y. It might be initially 1, and then it's going to drop from 1 down to 0. And then later it's going to jump from 0 back to 1. Okay? So you can see that each signal has a waveform. The waveform shows the value of the signal as it is changing over time. So this is X, this is Y. These are the inputs, okay, to this AND gate. Now, because we have an AND gate, the AND gate is going to produce the output 1 when both inputs are 1 and 1. That's the AND gate, okay? So notice that initially when X is equal to 0, notice that how the output here, Z, is 0. And now when X and Y are both 1 and 1, you get the output is equal to 1. So as soon as X changes from 0 to 1, then Z, the output Z, is going to change from 0 to 1 because Y is 1. So we have X changing from 0 to 1 and Y is 1. So Z is going to become 1. Okay. Now notice that when Y changes from 1 down to 0, the Z output is going to change also from 1 down to 0. Okay. Because now we have Y changing, it became 0. So the Z is going to change, it's going to become 0. Okay, notice that here also how the Z is changing from 0 to 1 because we have X is 1 and Y is changing from 0 to 1. So this will give me the output Y is equal to the output, sorry, Z is equal to 1. Okay. So this is what I call the timing diagram. The timing diagram is very important, especially when you would like to verify the correctness of a given circuit. In this example, I'm just showing an AND gate, just one AND gate. Okay. Do you have any question about this timing diagram?
Doctor, this diagram is for the simulation of the circuit, right?
Exactly, exactly. So we can use timing diagrams to simulate any circuit. Okay. And here, for simplicity, I'm just showing one AND gate. Now, notice that I said that this gate has 0 delay, which means that when X changes from 0 to 1, exactly at the same moment in time, I have Z changing from 0 to 1. So notice that how Z is changing from 0 to 1 instantaneously, because the delay here is assumed to be 0. Now, this is not really real. Yani gates, they do have delays, even though that their delays is very small, but we cannot ignore these gate delays. In this example, I'm assuming that the delay is 0. But if the delay is not equal to 0, I have to show it in the timing diagram. Okay, so let us take a look here at this example. Now, the gate delay here is given by this parameter, which is tau. For example, we can measure the gate delay in, let us say, nanoseconds or picoseconds, depending, of course, on the technology and how fast are these gates. So if the gate delay is tau, okay, and this is the same AND gate, but we're assigning to it a delay. So notice that when X changes from 0 to 1 here, the Z is not going to change from 0 to 1 instantaneously. It's going to wait for tau before it changes from 0 to 1. Okay? So that's the gate delay. So it shows that Z is going to change, but not instantaneously, but after a certain delay. That's the meaning of the gate delay. Now, the gate delay is that because we have transistors inside these gates. And these transistors don't switch instantaneously. They have a certain delay. So this is the meaning of the gate delay. Similarly here, for example, when Y changes from 1 back to 0, down to 0, notice that Z is changing from 1 down to 0, but after a certain delay, which is tau. So you can see that the waveform is shifted to the right by tau, which is the gate delay. That's the meaning of the gate delay. Okay?
Okay, clear.
Right. So we are going to later, we're going to describe our gates in Verilog. And you will see that in Verilog, you can assign delays for these gates. And you can look at the timing diagram, and you can see that how the delay of the gate is going to affect the timing diagram. Right. Let me talk about the propagation delay. Now, that was the delay of a single gate. This is why we call it gate delay, because it is just for one gate. Now, how about a circuit? In the case of a circuit, you have many gates, and each gate will have a delay. And sometimes the delay of different gates is different, depending, of course, on the gate itself. So the meaning of propagation delay is the delay inside the circuit between the inputs and the outputs. That's the propagation delay. Now, the propagation delay can be different on different outputs. And you might actually have multiple outputs in a given circuit, and you might get different, propagation delays. For this reason, in order to define a single number, which is the propagation delay, we look at the longest delay inside the circuit. So we define here the propagation delay as the longest delay inside the circuit along the critical path. So the critical path, it is a path inside the circuit that has the longest delay. This is the meaning of the critical path. So what we have to do is that we have to compute the propagation delay. We start at the inputs, and then we look at each gate inside the circuit, and we look at the maximum delay at any input inside, at any input for this gate, and then this is what we call the maximum input delay, and then we add to it plus here the gate delay. So this will give me the delay at each output, okay, at the gate output. Now, if you would like to find the delay, the propagation delay of a given circuit, look at the maximum delay at any output, and that will give you the propagation delay of a circuit. Okay, I'm going to show you an example. Of course, this is just a description of the propagation delay. Let us take a look at this example. Now, in this example, I have some of these gates are AND gates. Some of them are 2 input, 3 input. You can see here I have 3 inputs. Here also I have 3 inputs. This is only 2 input. I also have OR gates. Some of these OR gates are 2 inputs. Some of them are 3 inputs. So we have different types of gates. Now, it turns out when a gate has a large number of inputs, as you increase the number of inputs to a gate, this is going to increase the delay of a gate. Now, suppose that we measure the delay of each gate inside the circuit, and this is given to us. It says that the delay of a 2-input AND gate is given as 2 nanoseconds. So for simplicity here, okay, I'm just showing here numbers like 2. It might not be 2. It could be like, for example, 2.1 or 1.9. It does not really matter. But this is given to us, okay, as 2 nanoseconds. Today, for example, in modern technology, you can actually have the delay not in nanoseconds, even in picoseconds. But for simplicity, I'm showing these numbers here in nanoseconds. Now, the delay of a 3-input AND gate is given as 3 nanoseconds. So it's not the same. Okay, it takes longer. Okay, so therefore it is slower, the 3-input AND gate. So the delay inside the gate is longer, and therefore it takes more time for the output to change in the case of a 3-input AND gate. Also, in the case of the OR gate, if it is 2-input OR gate, the delay is 2 nanoseconds, the same thing as in the case of the AND. And in the case of the 3-input OR gate, it is 3 nanoseconds. So you notice that these delays are not the same. Okay. So the question is, compute the maximum circuit delay. So that's the propagation delay. Okay, so to calculate the propagation delay, we have to find the maximum circuit delay. How do I do this? How do I calculate the maximum circuit delay for this given circuit?
Take the maximum delay for each and every gate you have in the circuit.
Yes. And then?
The maximum delay of the outputs is the maximum delay of the circuit.
Right. I'm going to show you now. Yeah. Okay. But how do we calculate this? I will show you a technique, an easy way to calculate this. It's not really difficult at all. Okay. It's really very easy to calculate the maximum circuit delay. So let me show you how we can calculate the maximum circuit delay. As I said, it's very simple, very easy. Right. We're going to assume initially that all the inputs to this circuit are present at the same time. So all of these inputs here, if you have 8 inputs here, for example, all of them are present initially at t equal to 0. So I'm going to assume that all my inputs are present. Okay. Now, if all these inputs are present, we look at the delay of each gate. Okay, as Osama said. So we're going to write here 2 nanoseconds. That will be the delay of the first AND gate. This will be 3 nanoseconds. This will be 3 nanoseconds, right? So the output of the first AND gate will be available after 2 nanoseconds. The output of the second AND gate will be available here at 3 nanoseconds. And the output of the third AND gate will be also available at 3 nanoseconds. Do you agree?
Yes.
Okay, good. Now, let us take a look at this OR gate, which is shown here. This OR gate has a delay of 2 nanoseconds because it's a 2-input OR gate. Now, tell me, what's the delay of the output of this OR gate?
5.
Why?
Because we have the second AND gate 3 nanoseconds.
Yes.
And the 2 input OR gate 2 nanoseconds. But
so we go by the exactly Nawaf. Yes, you are right. So we go by the maximum. So we go by the maximum here. So the maximum of 2 and 3 nanoseconds will be 5 nanoseconds. Sorry, it's the maximum will be 3, and then we add to it plus 2 will give me 5 nanoseconds. Correct? So what we did is that at time equal to 2 nanoseconds, we get the output of the first AND gate, but we did not really get the output of the second AND gate. So we have to wait for 3 nanoseconds to have both inputs to this OR gate. Correct? So we have to wait for both inputs. And once we have both inputs at equal to 3 nanoseconds, we add 2 nanoseconds, and this will give me 5 nanoseconds, which is the output of the first OR gate. Fine. How about the second OR gate?
6.
Yes.
Well, we know that actually the delay of this is 3 nanoseconds. And yes, we know that we have here 3, here we have 2, here we have 3. So we have to look at the maximum delay at any one of these inputs. So we get 3, and then we add 3, we get 6 nanoseconds. Do you agree?
Yes.
So this is really easy. Right. For this AND gate, we have 2 inputs.
2 nanoseconds.
We go by the maximum delay at any input, which is 6. Here we have 2 nanoseconds. So the output will be present at what time?
8 nanoseconds.
Exactly 8 nanoseconds. So notice that the output at G, you can guarantee that the output G will be present after 8 nanoseconds, whereas the output F will be available at 5 nanoseconds. So what is the propagation delay for this circuit? Is it 5 or is it 8?
It is 8.
Yes, because at time equal to 8 nanoseconds, we can guarantee that both F and G are present. At t equal to 5, we have F, but we don't really have G. So we have to wait for both of them. And this is why we have to wait for 8 nanoseconds. So this is why the propagation delay is defined as the maximum circuit delay. That's the meaning of the propagation delay. Okay? Fine. So we understand this problem. Okay, we know how to calculate the propagation delay. Now, can you tell me, okay, let me clean up this again, erase all the ink. So you can see that how you can look at the delay at the output of each gate inside the circuit, and the maximum delay is 8 nanoseconds. That's the propagation delay. Now, if you look at these gates, you can see that if I would like to number these gates, suppose that I number them as 1, 2, 3. Here I have 4. Here I have gate 5, and this is gate 6. I'm just assigning them numbers. Can you tell me what is the critical path?
From the gate number 3. 3,
Okay,
5, 6.
so can you tell me all the gates along the critical path?
Yeah, 3, 5, and 6.
Excellent. So we have here 3, 5, 6. These 3 gates are along the critical path. Is there another critical path?
Yes.
Yes.
2, 5, 6.
2, 5, 6. So we have discovered more than one critical path. Okay. So the meaning of the critical path, these are the gates that will give you the longest delay. Sometimes you might actually have more than one critical path. Is 1, 4 along the critical path?
No,
Is
it
1,
isn't.
4? It's not. Okay. It does not really give you the longest delay. So 2, 5, 6 or 3, 5, 6 are along the critical. These define the critical path. Okay. Now, another thing about signals is the rise time and the fall time. Now, so far what we have seen an ideal wave. So the meaning of ideal, it means that it's a square wave. So notice that how the the signal is jumping from 0 to 1, is jumping instantaneously. And notice that how it is dropping from 1 down to 0, it's also dropping instantaneously. So it jumps from 0 to 1 in 0 time, and it drops from 1 down to 0 in 0 time. Now, this is not real. This is how logic simulators will draw the waveform. Okay, they will not really show the rise time and the fall time. A real wave is shown below. So notice that how it takes time for the signal to go from 0 to 1. So this is what I define here as the rise time. So the rise time is defined, okay, for a given signal. It's the time which is taken to change from 10% to 90% of the high voltage. Yani, for example, this is 10%, and this is 90% of the high voltage. So the time in between is what is called the rise time. If you would like to define the fall time, you look at the time it takes to drop from 90% to 10%, and this is how it's defined as the fall time. So these actually can be measured, okay, for a given signal. So it takes time for the signal to jump from 0 to 1, and it takes time to drop from 1 down to 0, or from high voltage to low voltage. So we can define the rise time and the fall time if you look closely into these signals. Okay. For us as logic designers, we will assume that the rise time and the fall time is 0, and the wave becomes ideal. So when you get the output, okay, for a logic simulator, we will see the ideal wave as a square wave. But this is not real. The real thing is that there is actually rise time and fall time, even though the rise time and fall time can be very small amount of time, but they should not be ignored. Okay, so when you would like to analyze the signal, you would like to look closely, and you can see that the signal, how it's going up and how it's going down. So we have a rise time and we have a fall time. Okay. Another thing that we should worry about is what was called the fan in and the fan out. The meaning of fan in is the number of inputs to a gate. And for example, we have seen in the previous slide, we have a 3-input AND gate. So when you have a 3-input AND gate, we say that the fan in is equal to 3. If you have a 2-input AND gate, we say that the fan in is equal to 2. If you have a 10-input AND gate, we say that we have the fan in equal to 10. So that's the number of inputs. Very simple. That's the meaning of fan in. Now, the problem with gates that have a large number of inputs, so increasing the fan in increases the gate delay. So when you have a gate that has 10 inputs, then this gate will be much larger than the gate that has only 2 inputs. And therefore, the delay of the gate is going to increase. So this is why we have seen in the previous example that the 3-input AND gate has a higher delay than the 2-input AND gate, even though it's made using the same technology. Okay, the number of transistors is going to increase inside the gate, and the delay is also going to increase. Okay, when we increase the number of inputs to a gate. Now, why people use gates with higher fan-in? Of course, I can implement, let us say, everything using 2-input AND gates. Yani, for example, I can implement, let us say, a 3-input AND gate using 2-input AND gates. However, using a higher fan-in, yani, for example, using gates that have 3 inputs or 4 inputs, it's useful because it can reduce the number of levels and the depth of a logic circuit. So when you use a 3-input AND gate, it's better sometimes, well, it is better than having a 2-input AND gates, because you can reduce, rather than putting 2-input AND gates in series, this would increase the propagation delay. You can decrease it by having 1 3-input AND gate. So that's the advantage of having gates with a higher fan-in. That's the meaning of fan-in. Okay. We also have fan-out. So what we have seen in the previous slide is fan-in, which is the number of inputs to a gate. What's the meaning of fan-out? Well, we look at the output of the gate. Okay, so fan in, we look at the inputs, the number of inputs. In the case of fan out, now you can see that the gate has one output here. Of course, does not really have multiple outputs. This is an AND gate. But you look at how many, this output is connected to the inputs of how many gates. So the meaning of fan out, it's the number of gate inputs that a gate is feeding. Yani, for example, this AND gate is, its output is connected to the inputs of 2 OR gates. So we say that the fan out is equal to 2 in this example. So sometimes in a circuit, you might have the same gate, its output is connected to the inputs of many gates. So the fan out can increase according to the number of gate inputs. So this gate is called the driver gate because its output is driving the inputs of other gates. So if the same output is connected to the inputs of many gates, then this is going to increase the fan out. Okay, that's the meaning of the fan out. Is this a problem? Well, it turns out that yes, okay, it is a problem. Why? Because each gate has a limited amount of current it can supply. Yani this AND gate, which is shown here, can only provide a limited amount of current. Now, this limited amount of current is going to be split among the 2 OR gates because some of this current will go to input 1 and some of this current will go to input 2. Okay. Now, if you have, let us say, if you increase the fan out, you have input 3 and input 4 and so on, then you are trying to split this current, okay, into smaller currents, okay, to drive these the inputs of the load gates. So I call these OR gates here are the load gates because this is the load, okay, for this AND gate. So because we have a certain amount of current, so each gate needs to consume a certain amount of current in order to switch, to change its output. Now, if the driver gate can only supply a limited amount of current and you increase the fan out, then each gate is going to receive less current. And for this reason, okay, at some point the circuit will not really work properly. So for this reason, we have to limit the fan out in a given circuit. Okay, so you cannot really have a very large fan out. You cannot really have a fan out which is equal, let us say, to 10 or 100. And the reason is that the limited amount of current that is produced by each gate. Now, the way that circuit designers use increase the fan out, they use special gate, which is called the buffer gate. Now, the buffer gate is drawn like an inverter, but it does not do any kind of inversion. This is a buffer gate, which is shown here. The input is X, the output is also X. So the output is equal to the input. So what is the advantage, or what is the benefit? Sorry, the benefit of having a gate whose output is equal to its input. Now, this buffer gate, its benefit, it provides, it amplifies the input signal. It can provide a high current output. Yani, for example, if I would like to have this AND gate here, okay, it has a large fan out, which is equal to N. So you would like to connect the output of this AND gate, okay, to the inputs. We have here N inputs, okay, of N gates. So all of them are load, okay. So if you would like to increase this fan out to N, for example, you can use a buffer gate. So the buffer gate will take the small current output of the AND gate and it will amplify it to produce a high current output so that this current can drive, okay, the inputs of all of these N gates. So this way we can, okay, we can use them to drive all of these N gates and increase the fan out. So that's the benefit of the buffer gate. So when you have a large fan out, we use buffer gates for that purpose. Okay, the main reason is to increase the current output, to have a high current output, and to increase the fan out. The only problem with this buffer gate is that we are introducing an extra gate in the circuit is going to increase the propagation delay of the circuit, because this buffer gate itself has a delay, and therefore the delay will be increased from the input to the output. So therefore the propagation delay is going to increase.
So it's also will increase the level, right? The level.
Yes. So exactly. So we're actually adding an extra level. So the importance of the buffer gate is that it can have a high fan out and it can supply a high current output. This is the reason why people use buffer gates.